Good morning, everyone. It's Charlie Jordan here again, bringing you another lesson in Algebra II Trig. This week we are leaving exponential and logarithmic functions and we're moving to trigonometric functions because we're moving on to essential concept number 3. Specifically in essential concept number 3, we're going to focus on evaluating all 6 trigonometric functions and with their ratios of the sides of the triangle and also using a unit circle. So let's go ahead and dive right in. Back in geometry, you learned about SOHCAHTOA. And when I say SOHCAHTOA, you hopefully know that I mean the ratios with sine, cosine, and tangent. Sine is the ratio of the opposite side and the hypotenuse side. Cosine is the ratio of the adjacent side and the hypotenuse side. And tangent is the ratio of sine and cosine, or opposite and the adjacent sides. So let's actually see what this looks like in a problem. It is officially our favorite time of the year, Christmas. Believe it or not, we'll be there before we know it. And it's time to hang icicle lights. You've moved to a new house, you don't have a ladder. You need to buy a ladder. You know that the roof of your house is 9 feet above the ground, right? Okay, so according to OSHA, you know that you need 3 feet of ladder above the roof line, and then whatever is your working part of your ladder, the part that you're actually standing on, that you need at least a quarter of that distance away from the foundation of the house to achieve the appropriate angle to be safe. So your question is, what is the shortest ladder you can go buy from the hardware store? Because we know that it's Christmas and we're on a budget, right? We don't want to spend any more money than what we have to. So we have a diagram. We're taking.
I have known since I was in 4th grade that I was going to be a teacher. I really just truly enjoy coming to work every day and working with different sets of kids and just watching them grow and learn.
I couldn't see myself doing anything other than teaching children, being a part of children's lives, being able to inspire them in a way that some people just aren't able to do. And to know that every day is a new day, a new opportunity to make a difference in the child's life means everything to me.
And we're back. Okay, so OSHA provides us with this beautiful diagram. Here we have our ladder, here's our roof. We know that the distance from the ground to the roof is 9 feet, right? Okay, so we need to determine what is our ladder length. Guess what shape was formed here? A triangle. Let me tell y'all something, those of you who are going to take the ACT. You'll have 4 trig questions on the ACT, and guess what kind of problems that they love to put on there? Something with a ladder leaning up against the wall or some kind of triangle. So pay close attention because you'll be able to use this concept when it comes time for you to take that test. So we need to determine the length of x, right? That's what we need to know because our question is, how big of a ladder are we going to be able to buy? What's the shortest ladder we'll be able to buy? So what can we use? Pythagorean theorem. You are so right. Pythagorean theorem and trigonometry go hand in hand. A squared plus b squared equals c squared. So we know that C is our hypotenuse, A and B are either one of the legs. So we can fill this in. We know X is our hypotenuse. So we can place X over 4 for A, 9 for B, and X for our hypotenuse for C. These could have been swapped. Doesn't matter which order you put them in. I just always usually use my smallest leg as A. It's up to you. Let's simplify this. X over 4 squared is going to become x squared over 16. 9 squared is going to become 81. X squared is going to remain at x squared. Now, if you're anything like my students, I bet you're like, oh my gosh, it's a fraction. I hate fractions. I love fractions, but I know that y'all don't like them. So let's go ahead and let's get rid of the fraction and make your job easier and more enjoyable. How are we going to do that? Multiply the entire equation by 16, right? Okay, when we distribute that 16 in, 16 times x squared over 16 is going to turn into x squared. 16 times 81 is going to turn into 1,296. And 16 times x squared is going to turn into 16x squared. So now, remember, the goal of an equation is to determine x. To do that, we need to isolate x. So how are we even going to begin that process when we have x's on both sides? we're going to move them together by subtracting this x squared from both sides, and that's going to result in 1,296 equals 15x squared. 15x squared, we need to get it to become a plain x squared, so we need to divide both sides by 15, resulting in 86.4 equals x squared. We also learned earlier in the year that to get rid of a squared, we're going to square root. But anytime that we put the square root in a problem, we have to include plus and minus, right? Well, in this situation, we're talking about the height of a ladder. So do we need the negative portion of the square root? No, because your ladder cannot be a negative length. That would be crazy, right? Okay, so we only need the positive square root. So we're going to square root both sides. Square root 86.4, and that's going to result in 9.30. That was really 9.29 and some other numbers, but it all rounded up to 9.30 equals x. So what is this answer here? What does it represent? Right, it represents the working height of our ladder, right? But how much more of our ladder do we have that OSHA requires? How much extra length? 3 extra feet, right? So we know that we really need a ladder that's at least 12.3 feet tall. Now, we're going in the hardware store, we're looking around, we see 5 feet ladders, 6 feet ladders, 8 feet ladders, 12 feet ladders. Can we buy the 12-foot ladder? Absolutely not, right? We would be under their guidelines, which would be unsafe. We need at least 12.3 feet. We see a 22-foot ladder. No, we don't want too much. Guess what we find? A 16-foot ladder. So in the hardware store, you have found a 16-foot ladder. Our question now is, what is the farthest distance we can place this ladder away from the base of the house and be in OSHA's guidelines, having the 3 feet above and being a quarter of the distance away from the house? 16-foot ladder. How much ladder are we actually working with, though? 13 feet, because we have this 3-foot distance up here, right? So that means that we have a 13-foot height right here. So how are we going to find the distance away from the base of the house? Divide 13 by 4, 3.25 feet. That's going to be the distance away from the house. It's the farthest we can place it and still meet OSHA's guidelines. My next question for you is, how can you determine the angle of elevation? First, my question is, what is the angle of elevation? What do we mean when we say elevation? When we think about elevate, we think about going up, right? Okay, so our angle of elevation. So in this case, we're looking at our angle down here in the bottom, the angle of the ladder with the ground, that angle that's formed there. So that's going to be our angle of elevation. So how are we going to find this angle? How are we going to determine it? We're going to use our trig functions, right? All right, remember we have sine, cosine, and tangent. You can choose any of these trig functions, but which one would make our life probably the easiest? If I'm choosing strategically, which trig function am I going to choose? Which side measures am I going to choose? I don't know about you, but if I have a choice of working with whole numbers or working with decimals, I'm going to choose whole numbers every single time. So I'm going to choose 13 and 9. Looking at our theta, at the angle that is marked, 9 is what relationship to that angle? It's opposite, and 13 is the hypotenuse. So that means we're going to use sine as our trig function. So we're going to have sine theta equals 9 over 13. Remember from geometry that to get into our theta, we had to use what was a brand new operation to us. We'd never used it before. Remember, anytime we're solving equations, we're using inverse functions. So what is going to be the inverse of sine? Sine inverse. We're going to sine inverse both sides. That's going to result in theta equals sine inverse of 9 over 13. The great thing is your calculator will take care of this for you. Make sure you're in degree mode, type it in, and you're going to find out that theta is 43.81 degrees. So that's going to be the angle of elevation. Think about it. That's almost 45 degrees. That's a pretty safe angle. You can probably hang your icicle light successfully with no injuries. Always make sure anytime you're on a ladder that you have someone else there. Don't get on a ladder ever at home by yourself. Let's move on. So we talked about 6 trig functions in the essential concept, right? And we've only talked about 3. So where do the other 3 come in play? They're the reciprocals. So sine, cosine, and tangent all have sibling functions that are the reciprocal of their function. So sine has a reciprocal function that is known as cosecant. What does reciprocal mean? Reciprocal means that I'm going to take the fraction, I'm going to flip it, right? So if I asked you to tell me the reciprocal of 3/4, that would be 4/3, exactly. So if sine is opposite over hypotenuse, using our understanding of reciprocal, how can we define cosecant? We're going to take sine and we're going to flip it, right? It's going to be hypotenuse over opposite. Cosine has a function called secant, a reciprocal function. Okay, so once again, using our understanding of reciprocal, how are we going to define secant? Hypotenuse over adjacent. And lastly, tangent has a reciprocal function known as cotangent. So how are we going to define cotangent? Adjacent over opposite, right? Or cosine over sine. Now, one thing before we look at what these functions mean, an error that I do not want you to create, okay? Naturally, our brain pairs things together that sound alike. Cosine, cosecant, sine, secant, an S and an S and a co and a co. Naturally, our brains want to pair those functions together, but that's not the case, okay? Remember that the S cannot go with the S, the C cannot go with the C, all right? Sine's going to pair with cosecant, and cosine's going to be paired with secant. Then tangent will be paired with cotangent. But go ahead and be aware of that so that you don't create that bad habit of accidentally pairing sine with the wrong function or cosine with the wrong function. It just is a tendency that our brain happens to do. So how can we use these reciprocal functions? If I told you that sine is 3/5, how can we find the 5 remaining trig functions? Well, what is sine is 3/5? What does that tell us? We know sine is opposite over hypotenuse. So if we look at a triangle and we have this bottom angle marked, which side is opposite? Straight across is going to be 3, right? Okay, and then 5 represents our hypotenuse, which is directly across from our 90-degree angle. But what is this missing side? We need to know one more leg. How can we find it? Pythagorean theorem, a squared plus b squared equals c squared. 5 is our hypotenuse, so it has to be placed in the place of c. So 3 can go in the place of a. 3 squared simplifies to 9. 5 squared simplifies to 25. To get b squared by itself, we subtract 9 from both sides, resulting in 16. And to get b squared, to turn it into b, we need a square root, and we only need to account for the positive square root because we're talking about distance and length. So we know that b is 4. So our missing side is 4. But we still need to find the 5 remaining trig functions. We know sine is 3/5. What about cosine? It's adjacent over hypotenuse. What side is adjacent to our angle? Which side is touching our angle? 4. So cosine is going to be 4/5. What about tangent? Tangent, you can either say it's sine over cosine. That's a very important relationship to know, especially for those of you who are eventually going to progress to calculus. Or you can say it's adjacent, opposite over adjacent, which is 3/4. What about cosecant? You could say it was hypotenuse over opposite, or we could use the idea that it's a reciprocal function. We could look at 3/5 and we could turn that into 5/3. You're exactly right. What about secant? 5/4. And what about cotangent? 4/3. Knowing that these are reciprocal functions, we can use our first 3 functions to determine these 3 functions. Or you could have used a triangle the entire time. So, hang on to this idea because it's going to come back in next week and we're going to tie it together with what we're about to learn. The unit circle. What is a unit circle? It's a very important concept. The unit circle is a circle that is centered at the origin that has a radius of 1. Guys, we're going to look at how to develop our understanding of the unit circle instead of memorizing it, because if you memorize it, you're probably going to eventually lose it. So let's develop the unit circle so that you can carry it with you through Cal 1, Cal 2, Cal 3 as you progress on to college. So we're looking at this unit circle. It has a radius of 1. It's centered at the origin, right? Okay, so if I know it has a radius of 1, what is going to be this ordered pair over here on the right? 1, 0. What about the ordered pair on the left? Negative 1, 0. What about the ordered pair at the top? 0, 1. And what about the ordered pair at the bottom? 0, negative 1. Now, the unit circle has an infinite number of points, okay, along its edge. But we're going to focus on the 3 most common points. And we're going to do that by looking into quadrant 1. 45-degree angle is going to be the first one we look at. We need to know, what is this ordered pair here? How can we figure that out? We can make a triangle. If we drop a line from this top straight down to our x-axis, guess what kind of angle it forms? A 90-degree angle. It's perpendicular to that axis. Okay, so if we pull this triangle, so we know that there's a 90-degree angle here and a 45-degree angle. What kind of angle is left at the top? Another 45-degree angle, right? All right, we know that this red line is our radius, and in our definition of the unit circle, we knew that radius was 1. So we know that our hypotenuse is 1. What kind of triangle is this, other than a 45, 45, 90 triangle? It's an isosceles triangle, right? Okay, so maybe you learned about special triangles in geometry, and you're probably thinking, yeah, I did, but maybe you don't remember all the rules. That's okay, because we can use something that we know to help us determine the length of our sides if we don't remember the ratios that we developed in geometry for a 45, 45, 90 triangle. What are we going to use? Pythagorean theorem. Okay, before we can use Pythagorean theorem, we need to discuss this triangle. Across the bottom, we're on the x-axis, so we're going to represent this leg with x. Our leg that is vertical, we're going to represent with y, because guess what? Y is our vertical measure, right? So when we go and we look at, so we talked about it's an isosceles triangle. I'm jumping ahead of myself. I need to slow down. So we talked about it's an isosceles triangle. So we know that the 2 legs have the same measure. So let's represent both of them with x. When we look at the Pythagorean theorem, a squared plus b squared equals c squared, we know that a and b represent our legs. What are our 2 legs? X and x, right? C represents our hypotenuse. What is our hypotenuse? 1. So now we have x squared plus x squared equals 1 squared. How can we simplify 1 squared? It's just 1. What about x squared plus x squared? 2x squared. I need to get x squared by itself. How do I do that? Divide both sides by 2. X squared equals 1/2. Finally, I need to square root x squared and 1/2, but I only need the positive square root. So I'm going to square root 1. I'm going to square root 2. What is the square root of 1? 1. What is the square root of 2? The square root of 2. Why can that not be my answer? Because I have a square root in the denominator, right? And that is nasty. We do not like that. That is gross. So we need to fix it. Do you remember what we called it whenever we fixed a situation like this? Rationalizing the denominator, right? So we need to multiply the top and the bottom by the square root of 2. We learned about that earlier this year, right? All right, so 1 times the square root of 2 is going to be the square root of 2, and the square root of 2 times the square root of 2 is going to be 2. We got rid of that square root in our denominator. It's so much more beautiful. Oh my goodness. I love it. It's gorgeous. Okay, but what does this answer mean? This is our x and our y value, right? So now we know that our ordered pair is the square root of 2 over 2, comma the square root of 2 over 2. Using Pythagorean theorem, we determine that. Let's look at our next angle, 60 degrees. Once again, we still know that the radius is 1, and we can still form a triangle. So my question to you is, if we know this is 60, we know it's still a right triangle, so we know this is 90. What is the angle of that measure? What is the measure of the angle at the top? 30, right? So now we're talking about a 30, 60, 90 triangle. That was a special triangle we learned about too, right? But maybe we don't remember all the different ratios that we developed in geometry. That's okay. We're going to use a different idea of how to determine these side lengths. Watch this. If we extend our triangle, we now know that this angle is 60. This angle up here is 30. 30 plus 30 equals 60. So now I have a 60, 60, 60. That's equiangular. So what does that mean about my side lengths? It's equilateral, right? So if this side is 1, what do I know about my other two sides? They're all 1 as well. Now, here's the really cool part. This is where we're going to start developing our side lengths. If this entire bottom is 1, and I doubled this triangle to make the big triangle, what do I know about this one black base over here on this side? It's 1/2, right? Okay, so now I can use that idea to determine the length of my vertical side. Guess what I can use? Pythagorean theorem. X squared plus y squared equals 1 squared. What do we know about x? It's 1/2. What is 1/2 squared? 1/4. So 1/4 plus y squared equals 1. I need to get y squared by itself. I'm going to subtract 1/2 from both sides. That's going to result in y squared equals 3/4. Once again, I only need to account for the positive square root. Square rooting both sides, that's square root of 3 over the square root of 4. The square root of 3 simplifies to the square root of 3. The square root of 4 simplifies to 2. I don't have a square root in the bottom, so I'm good. I don't have to rationalize. I know my entire point is 1/2 common square root of 3 over 2. What about this 30-degree angle? If I know that this is 30 and I know this is 90, what do I know about my top angle? It's 60, so I have x and y. This is a 30, 60, 90 triangle. But didn't I just work with a 30, 60, 90 triangle? Yes, I did. So let's bring it back out and let's see if we can use this triangle to determine the lengths of this triangle. And we're going to be able to. So here are 60 degrees. Directly across from it was the square root of 3 over 2. On our triangle that we're actually working with, we know directly across from 60 is x. So now what do we know about x? X is the square root of 3 over 2. At our 30-degree angle, it's directly, the side that's directly across from it is 1/2. Over here on our triangle that we're working with, directly across from 30 is y. So what do we know about y? It's 1/2. So our ordered pair is the square root of 3 over 2, comma 1/2. Now let's apply this to quadrant 2. What is different about quadrant 2 from quadrant 1? Our x-axis is negative, right? Our y-axis is still positive. So what can we do to these ordered pairs? That's what we're going to look at. If we look at quadrant 2, this is our 45-degree angle or our 135-degree angle from the x-axis, positive x-axis. What can I do to the square root of 2 over 2, comma square root of 2 over 2 to make it applicable to quadrant 2? I'm going to change the x-coordinate to negative, right? What about our 60-degree angle? 1/2, comma square root of 3 over 2. I'm going to make the x-coordinate negative. What about our 30-degree angle? I'm going to make the x-coordinate negative, right? Same coordinates. The only thing is x and y are both positive. Now x is negative, right? Okay. What about quadrant 4? We're going to look at quadrant 4 before we look at quadrant 3. Let's compare quadrant 3 to quadrant 1. Y is now negative, x is positive. So what do we need to change about these ordered pairs? We need to make y negative, right? So that's what we did. Now let's look at quadrant 3. Let's compare quadrant 3 to quadrant 1. X and y are both negative, right? Our x-axis is negative, our y-axis is negative. So both portions of our ordered pair we need to turn to negative. And that's exactly what we did there. Okay? So let's talk about here, x and y are both positive. X is negative, y is positive. Both x and y are negative. And then x is positive, y is negative. Okay? Next week, we will pick back up using our trig functions and our unit circle. And then we're also going to learn about radian measures, and we're going to tie all of this together back to our 6 trigonometric functions. So make sure you tune back in next week to see how all of this ties up and wraps together. I'll see you next week.